Good morning, good afternoon, good evening. It seems like I haven't said that in a long time. We've been off for a few weeks, and we're very happy to be back. Not off of any particular reason, just scheduling, and also in some way on a personal note, I am sort of on a I am sort of training for marathon, not the regular kind, but I have a 10-day meditation retreat scheduled in May, which requires about 11 hours of sitting for 10 days straight. So, I've been motivated to train for that. But in any case, we are very happy to be back, and very happy to come back with DC Palter, founder and CEO of Apposite Technology, and also the presenter of one of the most probably I'm absolutely one of the most successful TV series of all, Shockfest.tv, and particularly talking about internet protocol. Good morning, DC.
Hey, Danny, how are you?
Hey, you look rested.
That's because I was in bed for a couple of weeks with a cold.
Yeah,
I'm getting better. Almost have my voice back.
I almost feel like we should just not talk about internet and just talk about Japan. We should probably have a show.
We could do a separate one. I'll give you my slideshow of me relaxing in the hot springs with lots of food all around me. That part of it was great.
Okay, and welcome to the show, Paul.
Hi, Danny. How you doing?
Very good, very good. You look great too.
Yeah.
So are you guys getting good weather in London these days?
We're on daylight saving time now, so it's light evening, and today has been breezy but sunny, so not bad at all.
Excellent. And Tim, how are you, sir?
Good morning. I'm okay. I haven't changed a bit so far.
No, actually, you have. You're looking good every day. You gained some weight.
At my stage in life, just being somewhere is fun. I did want to mention one thing. Next week I'll be part of the judging staff again for my 7th year at Kennesaw State University for the cyber the collegiate cyber challenge. That's the 7 finalists from the Southeast will be competing for a chance to be in the national runoffs.
Wow.
Come in a few months, and it's very interesting to be a judge and to see these kids do. They're kids. Anybody under 50 is a kid to me, but these youngsters do the things that are just amazing. But the challenge basically starts off: go into this room. That's your new network. The people that were in charge of that network were all fired. They're gone, and we don't know passwords or anything. Get your network fixed and up and running.
Wow. We should probably talk about that. We should talk about that.
It's really great. And I'll take some pictures, and I usually try to write an article. This year I'm going to take more pictures and write an article. I got to be careful being a judge, so but it's absolutely incredible to see these young kids. They are just incredible. And they don't even use a tap. Well, go there. I mean, it's great.
Really? Okay, well, so with that, I'm gonna turn the camera to DC and let him shock the world like he always does.
Thanks, Danny, and it's good to know that by Tim's definition, I am an adult. I hear that.
You're a youngster. Come on.
According to your definition of over 50, I am an adult. All right, so let me figure out how to turn on screen sharing here again.
So while you're doing that, let me just add in on the age discussion. So I was talking about how I'm getting my Mini Cooper, and I went to the dealership, and I said, my last car was a BMW, and I had it for 15 years. So I'm planning to have this for another 15 years, and I'll be 75 when that happens. The guy fell off the chair. Go ahead, DC.
All right. Can you see my screen?
Absolutely, sir.
Good. All right. So today's session is we're continuing on the fundamentals of TCP/IP networking. This is session 4, where we're going to start getting into the gory details of UDP and TCP. And in fact, UDP is not very gory at all. We'll be able to dispose of that very quickly. TCP is maximum gore, so that's actually going to take 2 sessions. We're going to do the first one today. Just to kind of put things in context, we started off with talking about networking in general, went on to TCP specifically, and then started getting into, we went through IP last time, so now we're going to start looking at the transport layer. I'm going to go through a quick recap of what we talked about with IP, because it's very important to understand the assumptions behind IP, because that affects the design of TCP and UDP. And then we'll get into the various aspects of TCP acknowledgements, windowing, transmission, congestion control, and session setup. Just a couple of notes. This is going to be a very simplified version of TCP. Obviously, we have, I don't know, maybe 30 minutes, where a detailed discussion of TCP would take days, if not weeks. But the point is really to give people a background of what's going on when you look at packets, when you look at packet traces, when you consider how applications are performing. So you're not writing TCP protocols. You don't need to worry about all of the gory details. It's important to understand in general what's happening, how does it work, and how does that affect applications. So we're going to leave out a lot of the kind of all of the various branches of what could happen under this situation and that situation, and focus on what's going to happen in the usual cases. And a second warning, today's session is going to talk about the original TCP protocol. Next time we'll start getting into some of the changes that have improved how TCP works, but today is going to talk about how it originally worked, just to keep things simple. So, you know, combining those warnings, you may listen to this, and if you're an expert in TCP, you'll say, that's not right. That's not how TCP works. In this case, it does this. In this case, it does that. Yeah, you're right. This is not completely accurate. It is a simplified version of the original implementation of how TCP works. So, you know, I don't want to get a whole bunch of emails telling me, you're wrong, you're an idiot, you don't know how it works. If you want to get into the details, there's the RFCs and the textbooks for that. My goal here is to make sure that people understand the basics. All right.
See, you're an entrepreneur. You're used to people telling you idiots. Don't.
Yes, that happens quite often. But usually they play stump the engineer or stump the sales guy, and they're often surprised to find that I am at least basically technical, and I can go through the basics of the important points that affect our product.
Well,
all right, so
you're also married, so you're ready for rejection.
Oh, well, yes, the answer to that is yes, you're right, honey.
Yes.
To pretty much everything. All right, so first we have our slide of the 7-layer OSI model. It is a legal requirement that all discussions of networking must start with this slide showing the 7 layers. However, I don't really like the 7-layer model, even though it's the official model. When we talk about the internet, when we talk about TCP/IP networking, the 4-layer model of network interface, IP layer, transport layer, and then application layer, and then the application itself makes a lot more sense. But either way, today we're dealing with what's called the transport layer. When we talk about layers, we also have to look at it as the way the layers are seen in the packets themselves. We have the Ethernet layer, where you have an Ethernet frame that has an Ethernet header. Everything inside of that is the Ethernet payload, and that includes what would be IP headers, TCP headers, application layer. From the Ethernet frame's point of view, everything is data. Same thing when we get to the IP layer, and then embedded with that we have the TCP layer, and then there may be applications layers within that. Wireshark does a great job of showing you the different layers, so that you can see what's going on within a packet. But it's good to look at the whole to be able to understand that there are separate layers within the various frames. All right. So our core protocols: IP, which transfers data across the network; TCP, which is a reliable transport for end-to-end communications; and UDP, which is an unreliable transport for end-to-end communication. I'm going to get into exactly what that means. But first, it's important to understand that when we have packets going across the network, TCP or UDP are strictly communicating end-to-end. They are the two end nodes communicating with each other, whereas what IP is doing is moving those packets of data from one side of the network to the other side. So traditionally, and things are changing with proxies and accelerators and stuff like that, but ignoring all that, fundamentally, we have the two end nodes communicating with each other using TCP or UDP, and IP moving those individual packets from one side of the network to the other. So it's important to understand how TCP and UDP work. It's important to understand how the assumptions that go into what that network looks like, meaning the assumptions of how IP is built. The first is that the network is unreliable. Not that that is a bad thing, but it's actually a good thing. All of this is in contrast to how telephone networks work, or traditionally worked, which was a reliable network. There was always a guaranteed connection between 2 points. With an IP network, a packet switch network, you can add or subtract networks at any time very simply. Every packet is treated independently from each other. If there's too much traffic, stuff gets thrown away. That just keeps everything nice and simple. Every node along the way is kind of a point unto itself. The network is stupid, and again, that's a good thing. That means we can have relatively inexpensive routers in the middle, and we can set those up quickly, and we can add and subtract networks easily, instead of the old-time network, which were these giant switching infrastructures. You had to build up whole buildings in order to be able to create a new network. So again, the intelligence is in the end nodes. That's where TCP and UDP are. The middle box is just moving packets from one point to the next point. And then lastly, stability is more important than performance. There's a lot of things that could be done differently and better, but TCP was designed for a network of a handful of nodes during the 70s and 80s, and it was really, we can even say it was kind of an experiment. It works, and it works very well. It's never collapsed, and we've made some improvements, but there's every year somebody comes along and says, let's throw away TCP and start all over again with something better. And yeah, we could come up with something a lot better if we threw away TCP and started over with modern internet, but it's not going to happen. We did that with IP. In fact, the same time that IPv6 was developed, there was a push to also develop a new version of TCP. And the consensus within the IETF was that both needed replacing, but IP was the more critical one because we were running out of addresses and routing space. And so let's get that done first, and then we can go back and redo TCP. As we talked about last time, that's been a complete disaster. We're still working on that transition. In fact, we're still working on starting that transition from IPv4 to IPv6. And the idea now of completely replacing TCP with something new and better has kind of gone way out the window. And so, there's occasional improvements to TCP that we'll talk about next time, but fundamentally the idea of a better, different transport protocol just isn't going to happen. So on to UDP, and we can keep this short because UDP is very simple. It's designed for real-time communications, voice, video, multicast, because that needs to go out to millions of sites at the same time, and so we can't have acknowledgments coming back. And then it was also designed for network management, and that was kind of a mistake that we've been dealing with since then. Things like SNMP are designed to run over UDP instead of TCP because the feeling that was a lightweight protocol and would use up less bandwidth. I think everyone acknowledges that's a mistake, and we've been kind of trying to find ways of convincing people to switch over all of their network management to TCP since then, but originally it was designed to run over UDP. Because this is real-time communications, there's no need for reliability. In other words, packets get to the other side, whatever gets to the other side, that's what we deal with. If we have a choice between sending acknowledgments back and telling the sender that stuff is missing, please resend it, and waiting for that to arrive before passing the stuff in order up to the sender, up to the receiver, or just dealing with what arrived. Obviously, for voice and video, we don't want to wait. So whatever gets to the other side, that's what we use. Therefore, there's no need to send any acknowledgments back to the sender, and that keeps everything very simple. So we call UDP an over-the-wall protocol. In kind of non-technical jargon, means the sender is just sending things over the wall. It doesn't know what got there, and it doesn't have any way of changing what it's doing. So whatever the other side gets, that's what it gets. Essentially, from a protocol point of view, UDP is a TCP packet with port numbers so that we can differentiate, multiplex different applications or different streams, and that's really it. There's no acknowledgments, there's no feedback from the sender, there's no rate control at the protocol layer to throttle transmissions, and there is a checksum, but it's optional. So our packet looks like this. We have a source and destination port number so that we know what application to hand it to on the other side. We have a length so that we know where the data starts, and then we have a checksum, optional checksum to deal with any packet corruption if we want to. And then we have the data, and that's it. So that's it for UDP. For UDP. Very, very simple. Now we get to TCP, which is kind of the opposite of UDP. It is a reliable, connection-oriented protocol. Again, thinking back to what I said about UDP, where we have a choice on the other side of dealing with what we get or telling the sender that stuff arrived or didn't arrive, and send the missing pieces. If you want to send a file to the other side, you had better get the entire file, and you'd better get it uncorrupted, in order, with nothing missing. And so we need a way of knowing what has arrived and what hasn't arrived, and for telling the sender what has arrived and what hasn't arrived, and resend the missing pieces. So we have two functions. One is we have to reliably send the data to the other side, and then TCP is also tasked with not overrunning the available bandwidth, finding a fair way of sharing the bandwidth between multiple TCP and UDP streams. It needs to do that over an unreliable network. Again, packets may be lost, packets may go by different routes and arrive out of order, and we don't know how much bandwidth there is because every packet could go over a different path. So how do we do that? So what we're going to do today is build a protocol. We're going to build up TCP from the beginning, from the point of view of how do we transmit data reliably between two end nodes over a network that is fundamentally unreliable. So our first issue is reliability. Receiver needs an exact copy of what was sent from the sender, and it may not arrive that way. So it needs to be complete, uncorrupted, in original order. So the first thing is, how do we detect corruption? Well, we have a TCP checksum for that. It is not optional. Every TCP packet has a checksum for the header and data. If the checksum fails, that packet is thrown away. That's it. Never gets to the application. And in fact, we don't even tell the sender that it was corrupted. We just throw it away. End of story. We also have packets arriving out of order or not arriving at all. So we need a way of knowing what's arrived and what hasn't arrived. And we do that with sequence numbers. The sequence numbers are by byte of starting from some initial random value that we tell the sender we're going to use. And then every byte is numbered. The reason we number the bytes instead of the packets is that when we resend packets, we may divide up the data differently. We may change the size of the packets so that one packet a resend packet may not be the same as the original packet. So we can't think in terms of packets. We have to think in terms of the bytes that are being sent. So every byte is numbered, and the receiver will tell the sender which packets, which bytes have arrived, and by converse, we can figure out which bytes haven't arrived. So we need a way of telling the receiver telling the sender what has arrived, and we do that with acknowledgments, which is a packet back from the receiver to the sender, and let's take a look at that. So we're going to start off building this very simple protocol, and what we're trying to do is provide reliability. And what we're going to do is when the sender sends a packet, the receiver will send an acknowledgement back to the sender. The sender knows that it's been received, and when it gets the message saying that packet's been received, the sender will send another packet. That is a very basic protocol. Actually, a lot of original transport protocols work that way. If you're on a LAN and you don't care about performance because the acknowledgements come back very quickly, that may be sufficient. When you're running over a WAN where there can be latency, the time from the packet to get from the source to the destination, the acknowledgement to get back from the receiver to the sender, that can cause some problems. So if we make a simple little calculation here, if we have a 1500 byte packet and we're going cross country, so we have about 1,000 milliseconds round trip, that will mean that we can only send about 120 kilobits per second as a maximum. So that's obviously not very good, but it works. And if our latency were, and the extreme went to 0, then our throughput could, in the extreme, go to infinite. So the amount of latency matters. If you're on a LAN, it's good enough. Over a WAN, effective but slow. Next thing we need to think about is what happens if one of those packets were missing. There's a number of different ways of dealing with this, and TCPs is not ideal, but again, it works. So what we do is the sender will send a packet. If it arrives at the destination will send an acknowledgement back, and the sender will send another packet. Now, if that packet gets lost, how do we know that it didn't get to the other side? Well, the receiver doesn't know that packet's coming, so it doesn't have any way of telling the sender that that the packet hasn't arrived. So we have a timer on the sender that it waits for an acknowledgement, and if it doesn't get an acknowledgement, then it gives up and says, okay, I guess it didn't get to the other side, so I'm going to resend it. The first question is, how long are we going to wait? It's a fairly complex algorithm, but the basic idea is we're going to wait 2 times the usual round trip time. Now, that may be a good estimate, or it may not be a good estimate. It may be that that packet's going by a different path, and we'll eventually get there in a longer time, but we're just going to give up on it. But that does mean that we need a way at the receiver of knowing what is a duplicate packet, and if we get duplicate data, we throw it away. So going back to the 1 packet and 1 acknowledgement at a time, again, effective but slow. The obvious solution to that is let's send a bunch of packets at a time. So we call that windowing, where what we're going to do is send a number of packets and wait for a number of acknowledgements. In our example here, we're going to send 3 packets, and so as each packet arrives at the other side, we wait for an acknowledgement to come back. The reason it's called windowing is we're only going to send a maximum of 3 packets. Now, the way TCP works, again, is not in terms of numbers of packets, but number of bytes. But to keep this simple, we're just going to think about a fixed size packet and numbers of packets. So we send a packet, we get the receiver sends acknowledgement, we send another packet, the receiver sends another acknowledgement. We have a maximum of 3, so once we've sent our 3 packets, we wait, we get an acknowledgement back, and when we get an acknowledgement back, we have We can clear that out of our buffer because we have to hold this in memory until we get the acknowledgement, because we have to be prepared to resend it. And then once we get the acknowledgement, we can throw that away. Then we have space in our buffer to send another packet. And we keep doing this until we go through all of the data. Theoretically, we could have a very, very large buffer and be able to send a very large amount of data. But again, TCP was designed a long time ago when the amount of data was smaller, the amount of buffers were small, the bandwidths were small, and that's kind of impacted the design of TCP. We also need a buffer on both the sender and the receiver, because the receiver could have gaps in what's arrived. So you could get, if you send 3 packets, it may be that the first one didn't arrive, but the other 2 did. So we need to hold the other 2 until we get the first one and can pass the whole thing off to the application. So both the sender and the receiver need to be able to buffer all of the data. So we call this the window size, and it's decided by the receiver during the connection setup, not by the sender. The original design limits that to a maximum of 64 kilobytes, so not very large, and that is the maximum within TCP. The individual implementations on the destination will decide what value to use, and originally that was in like Windows 90, 95, it was 8 kilobytes, and it gradually went up to 16 and then 32, and now I think 64 is fairly common. But that would affect how applications performed over the WAN. Oops. So our example here is a maximum of 5 kilobytes of data with that we want to send in total, with a 3 kilobyte window, and our packets of 1 kilobyte. And we can see once we get the 2 acknowledgements back, we've sent the next 2 packets. That's the end of our 5 kilobytes of data. We get acknowledgements back for those, and we're finished. So that the previous example said for every packet that arrives, we will send an acknowledgement. And that works, but a little bit inefficient. The way the TCP acknowledgement works is it doesn't acknowledge the packets that arrive. It doesn't say I received packets 1, 2, 3, and 7. What it says is that the last byte in order that arrived is sequence number X. What that means is that every packet, every acknowledgement acknowledges everything that arrived before it in order. It doesn't say anything about what may have arrived afterwards out of order, but at least everything that's arrived in order before it has been acknowledged. That means if a lot of packets are arriving quickly, we don't need to send an acknowledgement for every packet. So we'll wait up to 50 milliseconds usually and see if any more packets arrived. And if during that time another one's arrived, we'll send an acknowledgement back. In general, 1 acknowledgement is sent for every 2 packets that arrive. That was to save bandwidth back in the time when a small packet of acknowledgement may have been a significant amount of bandwidth if there were a lot of them. Nowadays, that's kind of in the noise compared to what's being sent in the forward direction, but that's still part of how TCP is designed. So back to our example here, we send 2 packets. The first packet, it waits before sending an acknowledgement. The second packet arrives, it sends acknowledgement for everything up to the end of packet 2. Same thing, 3 arrives, nothing happens. 4 arrives, we send an acknowledgement back for everything up to the end of packet 4. And then when the acknowledgement for packet 1 arrived, we can then send 2 more packets worth of data, and then we can get an acknowledgement for everything up to the end of packet 6. So what happens in this scheme when a packet is lost? So we look at our example here. We send packet 1, nothing happens. We send packet 2, it arrives. So we now have 2 packets. We send an acknowledgement back, and that allows us to send 2 more packets worth of data. In the meantime, we had a 4 packet window. So we've sent packet 3, it arrives. We wait for for another packet to arrive, but packet 4 has gotten lost, so it never arrives. So when packet 5 and 6 arrive, we send an acknowledgement saying the last byte of data that has arrived in order is the end of packet number 3. Packet number 6 arrives, and same thing, we send an acknowledgement back saying the last thing that arrived in order with no gaps is the end of packet 3. And you'll notice when there are gaps, when there are packets arriving out of order, we send an acknowledgement for every packet. We don't wait for every 2. But we keep telling the sender, last thing that arrived in order was packet 3. We don't tell them anything about packet 5 arriving and packet 6 arriving. Eventually, there's a timeout, and then we resend packet 4. That arrives, and now we've filled in the gap, and we've received everything up until the end of packet 7. So we send an acknowledgement back saying last piece of data that arrived in order was the end of packet 7. And that is the basic acknowledgement system for TCP. Next, we need to look at how we control the bandwidth. If TCP is sometimes may have the bandwidth all to itself, and we want to be able to use all of that bandwidth. But other times, it's sharing it with other senders, either on the same machine or other traffic from other machines that we don't know anything about. So we don't want to immediately blast the network with traffic, because if it's already congested, we're just going to cause overload. The basic assumption is that we don't know, TCP doesn't know anything about any of the other connections. Even if they're on the same machine, it doesn't know anything about those. Each connection is independent of each other. Network may be congested with other traffic, and sending lots of retransmissions may make it worse. Blasting it from the beginning may kill the network. So what we want to do is start our connection slowly and ramp up if there's no loss. Then if we hit a loss, we cut our rate and then ramp up slowly from there. So for new connections, we do something called slow start. We send a single packet. We wait for an acknowledgement. When the acknowledgement comes back, we say, good, we have some bandwidth. We can send more. So the next time we send 4 packets. And when we get an acknowledgement back for that, we said, great, that worked. We'll send 8 packets. We'll send 4 packets. And we'll keep doubling every time until we either hit loss, meaning our network, we've gotten to the level of congestion on the network and we need to slow down, or we get to the rate of half of the TCP window size. Once we reach those limits where we hit loss, or we get to half of the window size, then we go into something called congestion avoidance. So if we hit a packet loss, we immediately drop our rate back down to 0, and we start the process all over again. And then when we get to half of the rate where we saw that original packet loss, from there we will ramp linearly, not doubling each time, but adding 1 packet to the window size each time. That is very slow. So people often joke that slow start is actually fast, because it will double each time, where congestion avoidance is very, very slow, where it will only add 1 packet per to the send window each time. There's been a lot of changes to how these things work, both within the standards and how they've been implemented. But again, what we're talking about is the original protocol here. And you can see it's very sensitive to packet loss, because it will immediately drop its rate to 0 and ramp up from there. It's also very sensitive to latency of the network, because depending on how quickly those acknowledgments come back will determine how quickly it can ramp up and use the available bandwidth. And if you have long latency link, that means you often have a very long time when the transfer ramps up to using the bandwidth. It also is then very sensitive to the design of the upper layer protocols. If you think about FTP, it's sending a large block of data that can take a long time. It can actually ramp up, whereas something like HTTP, which sets up a new connection traditionally for every transfer, means that every time you are sending another another widget or another photo or element on the page, you're starting from the beginning, which is not very efficient. Again, there have been changes, but that's traditionally how TCP works, and at its simplest, that's what's going on. We need to open a connection. Fundamentally, TCP is creating two separate connections, one in each direction. So when we set up a connection, first we send what's called a SYN packet from the side that wants to open the connection to the other side. It will acknowledge that it's opening that connection and send a SYN to open a connection in the other direction. It combines those together into a single packet, which is called a SYN-ACK, and then the first side needs to acknowledge that it's opened the connection in the other direction. So we call this a three-way handshake: SYN, SYN-ACK, and then an ACK of the SYN-ACK. We can only start sending data once the connection has been established. So again, if you were designing for HTTP, you would start putting your data into the SYN packets and the SYN-ACK packets, but we don't. Those are separate packets. We wait till the connection is open before we send data. Closing, we have to close the two sides separately in the two directions, so we send a fin packet, finish, from one side to the other side sends an ACK that is closing the connection, and then it needs to send a fin to close the connection in the other direction. Again, not real efficient, but it works. And then there's also the possibility of sending a RST, a reset packet, to immediately shut down the connection in both directions. That we do this for when there's an error or something else going on. So this is what a packet looks like, a bunch of different fields. And so we have the source and destination ports. Again, these are to differentiate different application, different flows from each other. We have the sequence number, which is from the sender, is the first byte in the packet. We have for data going back, for the acknowledgement going back, that is a field in the header where we put the sequence number, really of the next byte that the receiver is expecting, an offset to know where the data begins in the packet, the flags to mark whether this is an acknowledgement or SYN or FIN or reset packet, the window size, the checksums for error correction, urgent pointer, which we don't want to talk about, the option field for some of the options that we don't want to talk about, and then padding to fill it out to a 4-byte boundary. So that is our first lesson in TCP. If you want to really get into the details, there's the RFCs for UDP, which is fairly simple, and TCP, which is fairly not simple. And then, of course, very good book where I've pulled most of this information out of, Comer's Internetworking with TCP/IP, which basically explains the RFCs in some detail. Next time, we'll start getting into the modifications of TCP that make it even gorier. So we'll start talking about some of the changes to slow start and to acknowledgements and retransmission mechanisms that have made it more efficient, but also made it more complicated. And then lastly, I want to take this time that you've allowed me to make a simple announcement that we're going to be at Interop. So anyone who's watching this, if you're coming to Interop, please stop by our booth at 2355. You can see a demonstration of our WAN emulators and show you what effect things like latency and packet loss have on application performance. But more exciting, we're going to have a new product announcement that I can't say yet, but we have a picture of our secret box here that we'll be talking about at Interop, and I'll be able to give you more details in our next presentation. And we'll be giving away some discount coupons for anyone who's interested in buying any of the emulators or one of our new super secret products. Thank you. I guess it's the time to open it up for questions.
Wow, I didn't even realize that we're less than a month away from Interop. We keep talking about wanting to do a show on that. It's already here.
Yes, we're less than a month away.
Well, before I open up for discussion, let me just extend an invitation to you, DC. Either this week or next week, or maybe even the week after. But anyway, right before Interop, let's do a show. And we just do it with Apposite technology. We could do it with other people as well, which would be Interop special. Just talk about the stuff that you'll be introducing. Just guide people through the show floor. How's that? How would that work for you?
We're getting a new product ready right now, so I'm going to be kind of
busy,
working 18 hours a day probably for the next month until the show. So if you don't mind, I would love to do that right after I get back from the show, and at that point I'll be able to talk about our new product and be able to show the same sort of demonstration that hopefully we will have working at Interop at that point.
That will work as well. I think to just
I really appreciate that offer.
Interop is one of our sponsors. Would really like to hit multiple birds with one stone.
We could actually even have someone with a computer at Interop set up a call with us, and you could be talking from Interop and showing us.
That would be great.
Yeah,
I get the same demo that we're doing at Interop. I'll be prepared to do here. In this sort of screen sharing thing afterwards. And Tim, you're going to be one of the first people to get one of these new products. I'm going to send it to you because you're going to love this thing, but I can't tell you what it is yet.
Oh, okay. Wow.
Yeah. Okay. Well, I'll open up the floor for questions. Paul?
Yeah. Really interesting. That's a great question, DC. It's quite pertinent to me because we're working on a TCP/IP training module at the moment. It's not as detailed as the type of thing that DC has just presented. The other thing that struck me was that we're coming at it from a different perspective because we started from a process-to-process communication perspective, whereas DC's come very much from a networking perspective, which is it's interesting. Just interested in the comparison.
And let me just interrupt you for a second. One of the reasons that Denny and I decided to do this series is we thought, and Tim as well, that there's a lot of IT people and networking engineers who really understand Cisco routers, and they know how to configure a network and set up a network, and they know how to read Wireshark traces, but they don't really understand what's happening in the communications between the protocols and how that then can affect the application performance. And so what we're trying to do here, this is a specialized audience, but that's exactly the audience of LMT, of networking people who, again, may not really have the understanding of how the protocols are working, either because that's not something they studied or because they had a class in networking back in college 20 years ago, and that's long forgotten, and no one pulls out their Comer book anymore. So there's plenty of classes that look at it from a computer science point of view. That's, I think, way too complicated and way too much gory detail for people who just want a short introduction of, I'm looking at my packet traces and I don't understand exactly why this is happening. And so that was really the point of this series, was to give an understanding at the protocol layer of what are those packets doing that are going over the network.
Yeah. DC just came back from a 2-week work holiday in Japan, and in Japan, if you want to be a sushi chef, you spend the first 3 years learning how to cook rice. So this this is really going back to the basics, right, DC?
No,
Yes.
no, don't get me wrong. It's not that I'm thinking it too simplistic. It's not, because in fact the version we're doing is even simpler than this, because there are things that DC goes into that we probably don't. All I'm saying is it's just a different perspective. It's just
yes, absolutely.
slightly different spin on it. The other thing, I did spot one thing. I thought I'd put this. I thought this is a bit nitpicking. But you said that the ACK number shows the sequence number of the last byte received. I think actually it shows the sequence number of the next byte expected.
Yeah, I think of it one way, but as you pointed out, it's actually the first byte that it's expecting to receive, not the last byte it did receive.
Yeah, it's all right. I'd be.
I'm off by 1 byte.
Yeah, that's right. The other thing is, interesting thing I found about UDP is I've used recently with NFS, which is NFS is Network File System, and it was originally designed to run over UDP, but I've seen tremendous performance issues running a modern NFS server and client over networks. It can tend to it suffers from all sorts of problems due to lack of flow control and really poor error recovery. So it's interesting the way there's been a swing away from some of the UDP towards TCP. And in fact, this was running on a Sun Solaris box, and Oracle now say don't use UDP, I believe, for NFS. So that was quite interesting. Another thing I was going to say was that with the reset packet, the reset flag, we often see reset flags as a normal end of connection. I know it's not intended in that, but you do see it a lot coming out of web servers, and I've always wondered why. And I heard somebody say that the reason for it is some form of security, improved security situation if you kill a session with a reset. I don't know what the truth is, but all I do know is if you're looking at a net trace and you're seeing lots of resets, don't assume that that indicates a problem. It could be quite normal. Those were just a few things I had, but yeah, really interesting. Well done, DC. It's good.
Thank you.
Thank you, Paul.
I think that when you look at TCP, UDP, or even the network protocols, it's a lot to swallow. It's like drinking water from a fire hose. And I like the way we're taking many steps. But the one thing I will tell people is don't muck around with UDP ports unless you know what you're doing. I had a guy telling me that all of a sudden none of his SNMP would work. And I asked him, what have you been doing? He says, nothing. He says, we did go in and clean up a bunch of ports that we didn't want to open. And it just so happened that 161 and 162 had been whacked. Well, guess what? None of your agents can communicate unless you set them up and they're able to look at a higher or different ports. But make sure when you muck with ports, you know what you're doing, because it can make more headaches than you can imagine. And
I suppose one of the most common uses of UDP, particularly with the audience who might be watching this, is for things like price distribution. A trading price distribution, any form of multicasting mechanism has to use UDP because, of course, TCP doesn't support one-to-many relationship, does it? It's just a one-to-one relationship. So that's where you see a lot, and obviously also on voice and video and things like that. But for data systems, we see it a lot in pricing systems and multicast type systems.
Mm-hmm.
TCP is monogamous once it's set up, and UDP is a bigamous. There you go.
That's one way.
Okay, well, with that, I think we should probably close the show. Yeah. Well, anyway, but we're also coming up on the hour mark, so I think it's a good time to close the show. Well, thanks again, DC.
Thank you for having me here.
Well, maybe we could piggyback 2 shows next time you do the Shockfest.tv. We could do the Shockfest.tv, and then immediately after we could tape one for the kind of recap of the interop.
That sounds great.
Yeah, and then just release it. That way, it's a good, efficient use of your time, right?
That sounds good.
Okay, well, so before I sign off, I would like to make a quick announcement. Paul will come back with his LMTV Tribe Lab in 2 weeks. And then, but next Wednesday, we have a new show that Tim and I have been working on. It's what we call LMTV Visibility. And it's meant to be a open forum for any one of us to talk about what it means to build a visibility layer. But it could also be a place where we introduce an interesting product and an interesting vendor. So in the past, I know we kind of make joke of Tim's preference on taps versus span port. We often kind of push it aside and say, well, that's just a personal preference. We even have discussions and wrote articles about how there are practicalities, and also I actually think of it more of a chain of custody. How important is the evidence to you? And if it's not that important, then let's not worry about the chain of custody. But if it is important, then there is no better way to do that than to use a tab. And with that, we're going to kick off the LMTV Visibility Show with one of our sponsors, Datacom, and they're going to come out and talk about one of their new product. Is it a 10 gig tab or 20 gig tab? I don't remember now, Tim.
No, you're off by a couple of decimals. It's a 40 gig. It's a new
40 gig. Okay, 40 gig. Okay, all right. Okay, so with that, we're going to close the show. Thanks again, DC. Thanks, Paul.
All right. Take care, everybody.
Everybody take care. Be good.
Okay, bye-bye. And see you next week.